Reggie, where are my vegetables right now?
Before we dive into new content that I hope you're all captivated for, we should schedule. Did everyone find and take a look at the study guide that was posted on Friday? If not, I highly recommend start to take a look at it because we have an exam on Friday and we're gonna have a study period in here on Thursday. And I have nothing planned for that, so there's going to be a lot of awkward staring between all of us if you don't come prepared with questions. So please come with, even if you just want more practice, and if any of that involves problems that I should prepare in advance so that I'm not trying to look them up and wasting our time, please let me know a day in advance. Also, first assignment is due Wednesday, but you can submit that as early as today. And the grader will prioritize in the order that they are received, getting those and turning them around back to you. The class is small enough that I anticipate that it should all be turned around to you. But the earlier you are in that queue, the sooner you'll get it back. I think that's just about everything for the moment. Does anyone have any questions about any of that or about where we are in the class or anything else of relevance that I can answer? All right. We will dive in then. Here's where the fun begins. So up to this point in this class, we have now 4 ways of showing that a language is regular. What were those 4 ways? What can we do? Yeah, DFA. We can write a DFA. Yeah.
You can do the same thing with an NFA.
Yep, NFA, that's 2. What are the last 2?
We could make a regular expression.
Regular expression, if you can find a regular expression, then the language is regular. And the 4th and final way?
Constructive grammar.
Yes, a regular grammar. Regular. So that restricted class of grammar that we talked about on Friday, if we can do any of those 4 things, or start with one, convert around, they're all equivalent to each other. We have an entire toolbox of ways to show that a language is regular. So yeah, construct a DFA or an NFA or a regular grammar or a regular expression. Any of those 4 will work. But we have, and I've hinted at this throughout the class, there is one thing we have yet to do, which is be able to show that a language is not regular. And that turns out to be way harder to do and involve a significant amount of thinking, construction, and overall pain. So we talked a little bit about what makes a language regular in general, and it's that we have a finite amount of memory. We can, for any string of an arbitrary length, it could be up to there's no bound on the length of a string that this language can represent, but with a particular amount of memory dedicated or given by the number of states in an associated DFA and the edges in that, or the number of productions in a grammar, or the size of a regular expression. Within that much memory, we can accept or reject any length string within that language, any finite length string. So that's how to think about this concept of regular languages. So to not do that, we need some way of showing that the amount of memory that we need scales with the size of the problem, or that there is not a bound to the amount of memory that is required to be able to accept or reject any string in that language. So as soon as there is some scaling factor to that, or we have to use some kind of memory trick, remember something about the structure of the input, then we end up needing to show that that is the case somehow. And one of the important pieces of information that will help you to be able to do that is a refresher to what I'm hoping most of you have seen in discrete, which is the pigeonhole principle. Who remembers or is familiar with the pigeonhole principle?
Vaguely, yeah.
All right, 2 or 3 people out of the class. we are really not doing our job in math.
Can't remember what it is.
Been learned under a different name.
That's unlikely, but maybe. So the basic idea of the pigeonhole principle is we're trying to shove n objects into k boxes and query the how many objects are the least number of objects in a particular box. So how many objects do we need in order for more than one box, or sorry, at least one box to have more than one object in it?
And there has to be more objects in our box.
Yeah, as soon as you have more objects than you have boxes, the box with the least in it, or the most in it, has to be at least 2. I think that's the way to state that. So if there are more objects than boxes, there are multiple objects in at least one box. There's no way to distribute them more evenly and have a box have every box have a single object in it. But we can extend this to the general pigeonhole principle and say that there are the ceiling of n over k objects in the worst case. So as soon as you have more than twice as many objects as you have boxes, there is at least one box with 3 objects in it, etc. So some examples. You are feeling really festive, so you go to Costco and get the really fancy, shiny sock box that has red, green, and blue socks, because those are obviously the only colors of socks that anyone would ever choose to wear. But given this, how many, so you wash your socks, you dry your socks, and in this dryer, it's just pitch black. You reach in, you can feel that it's a sock, but they all feel the same. How many socks do we need to pull out of the dryer in this blind, dark environment that computer scientists like to live in before you know that when you go back to the light, you have at least 1 pair of socks? And the answer is 4. Yeah, as soon as you have 4, you could, in the worst case, have 1 red, 1 green, 1 blue, and 1 that matches one of those. As soon as you have 3 socks, you could have pulled 1 of each color, in which case you're going to look absolutely silly, as if you didn't look silly just showing up to the workplace wearing red, green, or blue socks in the first place. At that point, once they're mismatched, it doesn't really matter if they're matched or mismatched. You look equally silly. Or equally awesome, depending on your perspective. How many people do we need in a room to ensure that at least 2 people share a birth month? This is not the birthday paradox of sharing the same. How many do you need in order to have more than a 50% chance of 2 people sharing the same birthday, which is less than you would think? That's the birthday paradox. But another pigeonhole principle question would be, how many people? 13? Yeah, that is the right answer. Since we have more than 13 people in here, it's guaranteed that at least 2 of us share the same birth month. Some people have talked about this already, as you can see by the fist bumps. How about how many people do you need in a room such that at least 5 people share the same birth month?
$61.
Close. That would actually be 6 people sharing the same.
Oh, no, because 12.
Yep.
5 times 12 is 60.
And then you would be.
Oh, yeah, that's 6. Yeah, you're right.
Yep.
49.
Yep, the answer is 49. You could distribute from January to December, the first 12 people in the room, then loop around and do it again. You would have 24 people, each person, you'd have pairs of people with each birth month. 36, you'd have triples of each person in the worst case. 48, you'd have 4, but as soon as you add that 49th person, it has to match with one of the groups of 4 of each of the months. So that would guarantee you at least 5 people share the same birth month when 49 people are in the room together. So let's start to apply this concept to the idea of regular languages. So we'll start with a language that we actually talked about in the first week as we were designing a grammar for this, just when we were introducing the concept of grammars, which was A to the n, B to the n, some number of A's followed by some number of B's. If it strikes you as strange that we haven't come back to this language that we talked about on the first week, it's because, well, it might not have been regular in the first place. So let's think about this. Is there any way with a finite amount of memory to represent a to the n b to the n? In a way that if n scales, we can still use that same amount of memory. Could you construct a DFA or an NFA or a grammar or a regular expression to represent this? What would that look like? And start to illustrate this in a way that might help this visualization. All right, so here's where we start. I'm not even going to bother to label these states because it's going to get out of hand really quickly. But so we need to be able to accept, you can imagine this is kind of a lambda transition for the moment as an NFA that allows us to just teleport to be able to read a to the 0, b to the 0. But as soon as we have a to the 1, b to the 1, there's no way to do that with just these two states. So we need to add some transition out here on an A, and then have that lambda transition that tells us that we are done now reading A's, and go back the other way reading B's. And we can continue this process, but these states can only handle now a single A and a single B. In order to handle another one, we need to continue this process and make another state out here on an A, decide that we're done reading A's, and now be able to work our way back. So now we can handle up to a squared b squared, AABB, but as soon as we have n equals 3, we can't represent it with this amount of memory anymore. So you can start to see how this entire process would just scale out to infinity in this axis. And every time we want to place, we could place a bound on n, and as soon as we placed a bound on n, it would be regular. If we could say that n is less than or equal to 5, then we just draw up to enough memory to store 5 A's, that we see 5 A's and 5 B's. And as long as we're less than or equal to that, we'll be somewhere in this diagram. But if n is unbounded, then we need an unbounded amount of memory to be able to represent the language. People buy that? Do you think that there would be some way with a finite amount of memory to represent this? Is there any way to get around this issue? It's not apparent to you, it's because it's impossible. And the only way we can say that it's impossible is not because I have an example of it, but because we have a process that we can go through that will actually show that no such construction is possible. And we need some tricks and tips to be able to put forth that kind of argument, because even as I have stated so far, this is not a proof that it is impossible. This is just an intuition. An intuition can lead us astray. It's a great place to start, but it is not a great place to end. So we need to utilize some math and try to figure out how could we actually show that a construction with some finite number of states cannot represent the entirety of this language. So if this were regular, then the DFA for it would have a finite number of states. That's true for every regular language. We can't make an infinitely sized DFA. We can't make an infinitely long regular expression or a grammar with an infinite number of productions, because eventually we need to be able to terminate and say, yes, the string is in this language, or no, this string is not. If we have an infinitely sized DFA, we have no guarantee that we'll ever be able to answer that question. In order for a language to be regular, every single finite length string needs to be accepted or rejected in a finite amount of time. So infinite number of possibilities for n, right? N could be from 0 or 1 or 2 up to the concept of infinity. Infinity is not a number, but there is no bound on the size of that. So because of this, we know that there are an infinite number of possible values for n, and there are a finite number of states. By the pigeonhole principle, there has to be at least one state where multiple values of n must map. We're going to go through the same set of states at some point to be able to answer this for two different values of n. Does that work? Does that make sense? Infinite number of n, finite number of states. We're going to go through the same state multiple times as we query this on different values of n. That's necessary in order to make that construction. So in general, from this point, we will just proceed with a proof by contradiction. We're going to assume that this is possible. Awesome. We can represent a to the n, b to the n in a finite number of states. Proceeding with that, we will create a logical contradiction by logic. And this is a little bit of an aside, but I love this concept whenever in any of my classes I start talking about logic, because this is a really important part of being part of a functioning society. I like making those random asides when I can, but a knowledge base like this is only pure and contains true information if every single one of those assertions, that amount of initial information, is true. So you can assert a single false piece of information into a knowledge base, and then using perfect logic, construct an infinite number of additional false statements. So there's nothing wrong with the process. It's just that you bought a single piece of false information without proof, which is crazy to expect of any person in today's digital age. The amount of information that we have to consume, there's no way for us to verify every single piece of information. But that said, we can use perfectly logical processes as soon as one person has lied to us or have interpreted a piece of information in a different way than it was intended because it's ambiguous. As soon as we interpret that, we can create an infinite number of falsehoods in our view of the world around us, based purely on correct logic. But it also creates a fun fallibility in any kind of knowledge base. If you are a hacker and you go put a single false piece of information in a knowledge base, that can propagate in ways that contradict the entire system, in ways that are really difficult to figure out. So proof by contradiction is exactly this idea. We're going to assert a falsehood into this knowledge base that this language is regular, and then we're going to go through the work using perfect logic to derive that if this were true, then we would create some kind of logical contradiction. Since everything else was true except for this one unknown piece of information, we can identify this one unknown piece of information as the culprit. That is what caused the logical contradiction that we found, since everything else was true and follows logic. So that's the general idea behind a proof by contradiction. If there's one thing we don't know, we'll just play around with it until we find an issue. As soon as we find an issue, you are the only unknown. So we will assume that there exists a DFA that accepts this language only if n equals some m that we are going to play around with. It's going to be how we instantiate this value of n. So a to the n, b to the n, we're just going to start by saying, all right, m is the number of states in the accepting DFA, whatever that happens to be. We don't know what that value is. One, it's impossible to construct, but by this proof of contradiction, if it were possible, that DFA with a finite number of states would have m states. So that's what this m is going to represent throughout this entire argument. The number of states in the DFA that accepts this. We can't instantiate that with like 7 because we can't construct a 7-state DFA because it's impossible. But if it were possible, then we would have a value for m. By the pigeonhole principle, that tells us there is some state in their Q such that the transition from the starting state through a to the n and a to the m is that same state. And since we know the DFA then accepts that language, there must be some transition from Q to the final state that only consumes Bs that gets us to that final state. But we know that there are two paths through this that hit that middle state with two different values of a to the n and a to the m. I'm going to break this down in a way that I think makes more visual sense in a second. But this is kind of the pigeonhole principle way of seeing it. Does anyone have any questions about this concept of why this has to be true if such a construction were to exist?
I think I'm kind of tracking the middle 2 points for me. I'm having trouble reading, but I assume when we get to the visual.
Yeah, so there are some finite number of states in this. We end up with an initial state Q0, we end up with some final state QF, and some middle state. Getting here consumes all A's. Getting here consumes all B's, and there may be some overlap between this. Maybe this state is exactly the same as this state. There's no guarantee of that in one way or another. But because there are an infinite number of values for n, and there are a finite number of states, then it must be by the pigeonhole principle that we can select two of them. There must be two of them somewhere where both of them reach this state after consuming their A's and before consuming their B's. So it has to be possible getting to this state that we could consume some number n sub 0. I'm gonna call this a to the x and a to the y. Two different numbers of a's to get to this state. And then since this is a to the n, b to the n, there has to be b to the x and b to the y as a possibility for getting from this middle state to this final state. So there is some state somewhere that consumes a different number of a's and a different number of b's at the same time and can still get to that final state. Yeah.
This would be if it were regularly.
Yes. Yeah, we're making this assumption because we're proceeding by a proof by contradiction that this language is regular. Therefore, a DFA with a finite number of states exists. Therefore, via the pigeonhole principle, because there are a finite number of states and an infinite number of strings in the language, that two different strings map to the same middle state after consuming some number of A's and or B's. And it doesn't necessarily have to be at the middle. There could be some B's here where we reach this middle point. There could be some B's here before we reach this middle point. The idea holds that we need different paths to get to this middle state. We can't always follow the same path because otherwise we would need an infinite amount of memory. We would need a different middle state for every single natural number, which we can't have with a finite number of states. Because there are a finite number of states, there have to be two different paths that consume the same number of characters to get to that same middle state in some capacity, somewhere between the initial state and the final state. That's all those middle points are saying. I'll have another way to think of it here in a second. So one thing to note that a DFA and or an NFA is just a transition graph. So we can think of it in terms of the graph terminologies that you've seen in an algorithms class. If a graph has no cycles, then it is finite. There are only a finite number of paths from a particular state to other states. It doesn't matter what the branching factor is. As soon as you don't have cycles, the size of the language, the size of the number of possible paths is finite. If you don't believe me, think of it in terms of a tree. Because we don't have any cycles, we can really we can treeify this graph. And I'm going to draw this from left to right. There's a little bit more room, but we have some initial state. And then how many states does this branch into? We can't have a self-edge, otherwise it's a cycle. So we can only have outgoing edges. Let's say we have two of those. So this goes to this state, this goes to this state. For each one of those states, we can't have any self-edges and we can't go back to this because otherwise we'd have a cycle. So this could have an arbitrary number of possible successor states here, but you can see that as soon as the graph is finite, then there are only going to be a finite number of paths through this tree. It's no longer really a graph. It's a tree. So in order to be able to represent any language with an infinite number of strings in a finite number of nodes, there has to be a cycle. Because that cycle has to be repeated in order to generate those infinite number of strings. As soon as I allow for a self edge here, now how many paths are there through this graph? You've created infinity. You can do this cycle any number of times. 0, 1, 2, 3, for every single path through this tree now, you can repeat this cycle 0 times, 1 time, 2 times, 3 times, 4 times. So with a single cycle, we've taken a finite number of paths through this graph, and we've turned it into an infinite number of paths through this graph. So the concept of a cycle is really important to this concept of a regular language versus proving that something is not a regular language. Because if a DFA is going to have a finite number of states and accept a language that has an infinite number of strings in it, there must be a cycle somewhere. How are people feeling about that? Can I describe that in any more detail or in some other way? Does that make sense?
Yeah.
All right, so yeah, if our graph has no cycles, we can represent a language with a finite number of strings in it, but not a language with an infinite number of strings in it. Any language with an infinite number of strings needs a cycle somewhere in the graph. So if there's a cycle with a non-empty label, I can speak, then the language must be infinite by nature. You can repeat that cycle any number of the natural numbers times whenever you get there. So as soon as there is a single path to that cycle, you've created the ability to represent an infinite language, a language with an infinite number of strings. So every infinite regular language has a DFA with a cycle in it. Yeah.
What do you mean by a non-empty label?
It means that in an NFA, you could create a cycle like this on a lambda. And since that doesn't consume any input characters, that doesn't change anything.
Okay.
So yeah, this has to have at least one character in the input alphabet in that edge in order to count as a cycle. Yeah. Great question. Anything else? So when we have a cycle, we can skip the cycle, which means iterate it 0 times or iterate it an arbitrary number of times. We're going to start using some terminology to represent these concepts because we can start to represent more complex concepts more succinctly in terms of the terminology that we use, but it's important to understand what they represent before we start using that terminology, otherwise that gets lost. So we're going to assume that this cycle has a label. Those are all of the input characters that are consumed when you run through that cycle once. So if some string W1, W2 is in the language, then the cycle has some label, and between W1 and W2 is where that cycle starts. Then we can now do what we call pump this string. So W1 is a path to get to the cycle from the start state. And W2 is the path from the cycle to the final state. So now I can start drawing this the way that I personally like to think of this, which is we have some initial state, and via some path, we get to another state. Then we can get from this state back to itself via some cycle. And it does not matter where this cycle goes or how many vertices it goes through, but we get back to this state in some capacity. And then we get from this state to an accepting state. These are kind of the 3 components of identifying a string that contains a cycle within it. So this is the concept of W1. This is the concept of W2. Getting to the cycle from the start state, getting to the final state from where the cycle ends. Because we need to be able to repeat that cycle, which means that we need to get back to it somehow. And then this becomes V, what can be repeated some number of times. So this tells us that W1, W2 is in the language because there is some path from an initial state to a final state. It iterates this loop 0 times. We could also have W1V, W2. That is also in the language. That's the string that iterates this cycle once. W1VV, W2 is also in the language. We have some definition, some way of finding an infinite number of strings that are in this language by breaking this down. And any infinite size language that is also regular must have this kind of construction in its DFA somewhere. It could be that W1 is empty and this cycle starts from the initial state. It could be that W2 is empty and that this cycle finishes at an accepting state. It could be that V is a single character and a self-edge, but V cannot be empty. The size of this loop has to consume at least one character. Questions on this? Does this help visualize the problem a little bit more, maybe? This is how I personally like to think of it. Rather than the pigeonhole principle, I actually prefer to think of it in terms of breaking it into these components. And we're actually going to replace the terminology for W1 and W2 here momentarily. The reason I use it initially is we've used W to represent strings, but we're going to turn this into XYZ momentarily. So yeah, you can repeat the cycle an arbitrary number of times to show that we know that W1, W2 is in the language, W1V, W2. You can put an arbitrary number of V's in the middle of W1 and W2 and pump this string, and every one of those pumped strings must be in the language as long as W1, W2 is in the language. We doing okay? We buy that? Any more explanation needed there? It is not a problem at all if you're feeling like, what, lost? Let's work this out. But I think starting from the intuition makes this make a lot more sense than starting from the math. So now I'm going to start using M to represent the number of states in this DFA, because this becomes how we're going to proceed with this proof. Here's a statement, and I'm curious if anyone can come up with the reasoning behind this. We know that we are going to encounter the cycle in this DFA by the time we have read M symbols into the input string. Why is that? Yeah,
Well, because M is the number of accepting states, right?
it's just the number of states
Or
in general.
states,
Yeah,
states, then the minimum amount of characters of a string would have to be in order to pass would be M. Since the loop is somewhere in between the beginning and the end, then it would have to.
yeah. I'll instantiate this M with 4 for the moment, and when we get into these proofs, please never instantiate M. I'm doing this just to make a point, but yeah, a proof is not a proof if you give me an example. But let's say this DFA has 4 states, and I'm going to draw them next to each other because it's easiest to visualize. We have an initial state, and it doesn't matter which of these states are final. It just straight up doesn't matter. When we read the first character from here, where could we possibly go? If we read the character and it happens to be a self-edge, oh no, we found the cycle and we're within the first M characters. But let's try to worst case this. This only goes one other place. If this has an outgoing edge to every other character, this is boring. But let's create the worst case of there's only one edge to the next character or the next vertex that consumes a single character. So great, we've consumed one character and we found a new node. We have not started a cycle yet. From here, we have some options. We can either create a self edge, which would, within one character of starting the string, we want to put this off as long as possible, finding this cycle. We could go back to this node, but that would create a cycle, reading A and whatever character that is to get back. So the only way to move forward and continue to read characters without having created a cycle is to move forward. Here, we could loop on itself, we could move back, but all of those create cycles. The only thing we can do is continue to move forward. But by the time we read that fourth character, because there are 4 states in this DFA, you can scale this idea to more states and more characters, but the idea is the number of states that are in the DFA, that's how many characters you need to read. As soon as you've read that 4th character, now we have to go back to some state that we've been to, be that this state or this state or this state or this state. There's no way to read that 4th character without having found some cycle. That make intuitive sense? Any questions on that as to why that is the boundary? So assuming that there are M states in the DFA, as soon as we have read M characters, we know that we have completed a cycle. Not just started a cycle, we know we've completed it. So as soon as we know that there's a single string in a language that somehow does not adhere to that property, we found some counterexample of some kind of string that when we go to do this and we go to pump it in some way, shape, or form creates a string that's not in the language, that it's not possible for that DFA to exist. So we are going to be searching through a very large search space, trying to think of and come up with some way to show that if this DFA were to exist, here is the general argument that would allow you to say that when we blow this up, by nature, there has to be this cycle. If we utilize this cycle some number of times, we create this string. This string cannot possibly be in this language by this language's construction, but it would have to be if such a DFA existed and this language were regular. That is the contradiction we are searching for. And if we find it, we have our evidence that the language is not regular. So let's dive into now the actual technical proof type of exactly how you're going to do that. And then I'll get you some examples. So as with many math proof types, you want to start by saying, let L be an infinite regular language, or L is the query language that we are looking for. We will say there exists some positive integer M, that is the number of states in a DFA that you could construct that represents L. There exists some positive integer M such that any string in that language where the length of that string is greater than or equal to the number of states in the DFA. As soon as we have more characters in the string than there are states in the DFA, we know there's a cycle in the DFA. We can decompose that string into these 3 components. Our old W1, V, W2 is now being represented as X, Y, Z, because I just think it's a little bit easier to grab than W1 and W2. X is going to be the portion of the string that comes up to the first time we see that cycle. Y is the cycle. Z is getting from the end of that cycle to a final state. There are 2 very important pieces that are going to be true or have to be true from this. We know that the length of X, Y must be less than or equal to M. Why? We've already stated this, but try to tie it into this language. What does the length of X, Y being less than or equal to M, what does that tie to that we've already discussed?
The number of times you loop through Y to consume more characters.
The idea we just drew out. By the time we get to the cycle and iterate the cycle, we can't have consumed more than the number of states in the DFA characters in the string. This was the 4 states in a row. We consumed, so there were 4 states in the DFA. By the time we consumed those 4 characters, we had iterated the cycle. So getting to the cycle and completing that cycle, the length of that has to be less than or equal to the number of states in the DFA. That's all that's stating. Same idea. M is the number of states in the DFA, like 4. Getting to the cycle and completing the cycle, the length of that can be at most the number of states.
Okay. Oh, so completing the cycle once, not
Yes.
arbitrary.
Yes.
Okay.
Just the length of the number of states that we visit. The number of characters that we consume in the input as we get to the cycle and complete the cycle. Yeah, that ends up being at most M characters, the number of states in the DFA. The length of Y has to be greater than or equal to 1. What is that referring to? Yeah.
You can't like finish the loop and then end the loop.
Yeah, the number of characters in the associated loop. We have to read at least 1 character in order to complete 1 instance of that cycle. So the length of that cycle has to be 1 or more characters. Such that we can now create a set of strings W that are X, Y to the I, Z, and that creates that entire set of strings. So XZ is W sub 0, XYZ is W sub 1, XYYZ is W sub 2, etc. We've created an infinite set of strings, each of which have a unique path through this DFA. Does everyone see that? Does that make sense? We have XZ making and we don't do this loop at all. We have XYZ that does. I'm just going to start drawing this. I really should draw this as a. We have this, and then 1 instance, and then that. Should draw this as final. We have XYYZ that does this. And so we just kind of create this list. So you can imagine this now as an arbitrarily long array of strings. This goes on forever. This doesn't actually ever close. Yeah,
Wouldn't XZ not be a part of the set though, because Y's length needs to be greater than or equal to 1?
the length of the loop in general, not necessarily the loop that is traversed. When we're looking at the analysis of the DFA, the length of that loop has to be at least 1. On a particular pass, we can choose to ignore that loop and go straight from the initial state to the final state, and that should be in the language. Great point, though. So now we have a way of generating an infinite number of strings that are in this language. So it makes sense now, if we can identify such a construct in the language, that if we picked an arbitrary one of these somewhere out here, we should be able to show that it is in the language. But imagine that it's not. We pick some string that's somewhere in this set, in this list, I should call it a list, and this string is not in this language, then this DFA couldn't have existed. And this DFA needs to have existed if the language is regular. So that's kind of how I'm visualizing what this is doing. So now every sufficiently long string that is in the language can be broken into these 3 parts. Getting to some cycle, iterating that cycle some number of times, and then getting from that cycle to a final state. That is true for every sufficiently long string in any language that is accepted by a DFA. So this is the way that we're gonna show that a language is not regular. So it's called the pumping lemma because we end up doing a lot of pumping, repeating of these y's, iterating this loop some number of times. We're going to expand this idea into an arbitrarily long string, and we just have to show that one of these strings in some capacity is not in the language. That's going to rely on some intuition on our part, because we need to construct this in such a way that it is possible to show that. And not all ways that you could construct this will show that. So we need to get some experience with this so that it's easier to see what you should do in order to be able to show this. I'm going to introduce one more way to think of this. And for some people this sticks, for some people it ends up messing them up a little bit. And for some people it doesn't work at all. So I turn this into a game, and I'll see if I can do this in 4 minutes. But it's phrased in the form of a game between 2 players, but it highlights exactly how we're going to go through this proof process. So player 1 and player 2 are playing the pumping lemma game. It is the world's worst game. If you find yourself playing this for fun, I will question what is wrong with you. But it identifies this concept quite well. Player 1 is going to pick a value for m. It's actually going to instantiate m. When you write a proof for this, don't do this. This is only for you to envision how to construct the proof or how to think about it. Please don't do this in your own written proofs for this. But you can imagine that player 1, the player you're playing against, is a bot. If it is possible for them to pick a difficult value of m for you to show, they will pick a difficult value of m. But they're going to tell you the number of states in the DFA. If such a thing exists, you can imagine them picking the correct value. Player 2 is going to say, okay, you picked this difficult value of m for me. I am going to select the string that is in the language that has to be of length greater than or equal to that m that was given to you. So this string is now selected. Its length is greater than the value that player 1 gave. Back to player 1. They need to decompose XYZ into and show, given this string, which portion of it comes from X, which portion of it comes from Y, and which portion of it comes from Z, but they have to adhere to these 2 rules. The length of XY must be less than or equal to m, that value that they picked in the first place, and the length of Y has to be greater than or equal to 1. Adhering to those 2 constraints, they can pick the decomposition XYZ however they want. If they do this really well, then player 2's life is challenging. So player 2 must pick the I, the number of times that Y is repeated, such that we generate a string XY to the IZ that is not in the language. If player 2 is able to do this, they win. If player 2 can't do this, then player 1 wins. The task that we're doing here, the real task, is showing that it is impossible for player 1 to win the game. That is what a real pumping lemma proof will show. It's not a path through this game that player 2 wins. It is showing that whatever player 1 does, they're screwed from the start. They're bound to lose, no matter what they do. So that's a real pumping lemma proof. But if you want to think of it in terms of a game played between 2 players, this might help you to come up with the intuition to write that general proof. That no matter if I take the role of player 2, player 1 can't win. Or if I take the role of player 1, then there's always something that player 2 can do to thwart my attempts to win. Does that make sense? I see this way too frequently in this class, that a proof that you give me on a homework is just an instance of playing this game. And as soon as you picked M as 7, then all you're stating is that no 7-state DFA exists, even if the rest of the proof is perfect. And if no 7-state DFA exists, does an 8-state DFA exist? You have not made any claim about that. a 12 state DFA, a 17,204 size DFA. So yes, if it is possible at all for player two to win the game. Wait, that's not what I want to say. I want to say it's impossible for player one to win the game, then the language is not right. That's actually lying. I need to change that immediately. Yeah, just because player one wins the game does not mean the language is right. I'm actually gonna go fix that immediately because we are out of time and we will come back. I will recap this. And we'll go into some examples to get you some experience working with this. Hopefully that didn't break too many brains. If it did, I have office hours starting now for your homework. No, I don't, in an hour. I have an office hour starting in an hour. Your homework. I have another class. Much as I'd like to go just 2 office hours.
It's so funny from the house down.